All right. So it's now, okay. Now, there's a question regarding the quiz, first quiz, and it's regarding the makeup quiz. If you were not eligible for the makeup quiz, I gave everyone a 0 for that. However, I set up the quizzes so that the lowest grade is dropped. So that grade automatically gets dropped. All right. Now, I don't know why anybody thinks their grade goes down by 10 points. I've checked. The overall quiz grade should be exactly the same as the grade that you got on the quiz. You check, you'll see that. Didn't go down 10 points. Now, the test that you took, the first test or second test, I've not adjusted it yet. I have to adjust it up so that the overall grade comes out correctly. So maybe that's what you're referencing, is the overall grade. Doesn't look right, but that's because of the fact that Canvas doesn't calculate your overall grade based on points. It calculates it based on percentages. So the fact that your test 2 has 110 points, and I'm counting that extra 10 points as extra credit. I need to adjust each of your test 2 grades up by 10% so that the overall grade for your tests are correct, and therefore the overall grade so far will be correct. So maybe that's what you're referencing to, but I've double checked the quizzes are being graded correctly, right? The 0 is being dropped. All right, so I don't know if you've checked on that, but does anybody have any questions about that? All right, so the test number 2, it needs to be adjusted. That's it. All right, I obviously would want to lower your quiz grade by adding that makeup quiz. That wouldn't make any sense. All right, so no questions about that? You all understand what I'm saying? Okay. Okay, so let us now, just give me a second here. I gotta. There we go. All right, I'm going to share the screen. We're going to be covering chapter 4. Oops. Give me a second here. Something's happened with my Zoom. 1 second. There we go. All right, should be able to share this now with you. All right, so chapter 4 deals with hypothesis tests. This is something brand new. Last week, we talked about confidence intervals. So confidence intervals are there to estimate the population mean, the unknown population mean or unknown population proportion with with an interval of values that are created from the sample statistics, whether it's a sample mean or sample proportion. Showed you how to do it. It's not, the formula for that is not complete yet. When we get into chapter 6, we'll have a complete formula for doing that. But this week, we're going to talk about hypothesis tests. And this is another type of inference in which a researcher, this is the type of inference that we'll see quite often, a researcher is interested in answering a research question. And their research question is challenging another question, or another statement of fact about something. And the research question is offering an alternative to that. So what we're doing is basically setting up hypotheses and then testing it with our sample statistics. All right, and step by step, I will show you how to do it. But this section 4.1 sort of introduces you to the idea of a hypothesis test. Now they have listed here some of the examples of research questions. Some of them are kind of silly, like are mosquitoes more attractive to someone who's been drinking beer? I don't know why anybody would be interested in that. But something that, a more realistic one would be something like a school district is looking at a new reading program, and they're testing to see if the new reading program leads to better reading among their students versus a current reading program. So that would be an example where they would set up a hypothesis about the new reading program. All right, so those are the types of things that we'll be looking at. Now, one of the examples that we'll be looking at in the book has to do with light during the night, and whether it actually has a bad effect by having light on when you're sleeping. This study actually was done with mice, not with humans, but let's take a quick look at it. Let's read through this and then show you basically the type of hypotheses that would be set up for this. All right, so it says here that numerous studies have shown that exposure to light at night is harmful to human health. So basically, a study was done looking at the effect of light at nighttime on body mass gain in mice. So if the mice are gaining weight at night as a result of the light on, this is not a good thing. All right. So anyway, this study involved 18 mice. They were randomly assigned to one of two groups, and there's two groups. One's called the dark group that had normal darkness when they were sleeping at night, and the other group had some dim light on at night, and that's called the light group. Okay. What was being measured is the amount of body mass gained in grams for the mice after 3 weeks of having this being in these groups. All right, so here's the actual sample data that was created, that was done from the 18 mice. Here are the two groups. There's the light group and the dark group, and these numbers represent body mass gains for these 18 mice in grams. Now there's more mice in the light group. I don't know why that they had 10 mice in that group and only 8 in the dark group. Maybe originally they had 10 in each group and maybe 2 of the mice died. That's possible. But anyway, they're the results right here for the 2 mice. Now this is an experiment because the mice were randomly assigned to the 2 groups. Okay, remember that random assignment. And so what is the research question basically? Let's just scroll down a little bit and let's take a look at it. All right. So there are 2 hypotheses that are typically done in a hypothesis test. One of them is called the null hypothesis, represented by an H for hypothesis with a little 0 and a subscript 0 next to it. It's called the null hypothesis. And that's basically, in this particular case, saying there's no difference between the 2 groups. That the average body mass gain for the group in the light that's getting light at night versus those who are getting regular dark at night, there's no difference between the 2 groups in terms of body mass gain. And the alternative hypothesis says that the body mass gain will be greater in the light group. That's a bad thing because it's considered a bad result. So the average weight gain, body mass gain for the group of mice is greater for the light group. So that's the alternative hypothesis. That's what the researchers are thinking, that the light group will have a worse result. All right, so one thing I wanted to show you also is the fact that we use mu here to represent the mean for the 2 groups. Now in a hypothesis test, we use the population parameter in the hypothesis test. We don't use sample statistics in the hypothesis test itself, because this hypothesis was done before any sample that was collected. So there's no sample statistics when somebody comes up with a research hypothesis. And anyway, in this case, we're comparing 2 groups, and we're looking at the average, the mean of the body mass gain for the 2 groups. And a hypothesis test is using the sample statistics to justify whether we should reject, this is the whole idea, we want to reject the null hypothesis, that's what the researcher is hoping, and hope that there's enough evidence to claim that the alternative hypothesis is true. because that's the research hypothesis. All right. So we have a null hypothesis, which is basically the status quo. And the alternative hypothesis is something that's challenging the status quo. Right. So now let's take a quick look at the sample results for the study. When they averaged, the average of the light group, if they average these 10 numbers here for the light group, they got 6.732. That's the sample average. And the average for the dark group, the average of these 8 numbers here, is 4.114. What they're really looking at is the difference between these numbers. Light group minus the dark group. We subtract these 2 numbers. That would be the difference in their means. And we want to know if that is enough evidence to suggest that the light group tends to have more body mass gain than the dark group. Here's a dot plot that basically graphs the 2 groups. Okay, and notice, of course, that the dark group has on the whole lower weight or body mass gain than the dark group. It's more spread out for the dark. Okay. All right. So we have 2 hypotheses, the null and alternative hypothesis. This is how we write the null hypothesis. We write it as H sub 0 colon, and then we state the hypothesis in symbols. And the alternative hypothesis is H sub A colon, and we state that hypothesis. All right. Now I'm going to show you some more examples. But this is in the book, they explain that the null hypothesis is claimed that there's no effect or difference. And the alternative hypothesis saying that there's some significant difference between, in this case, between the 2 groups. All right. So again, don't worry about the terminology yet. As we I show you more examples, you'll get an idea of exactly. All right. Here's an example here with proportions. Suppose that you're a server at a restaurant, particular restaurant, and you're making a claim that you think that of all the diners who ask for going home boxes, that's for leftovers. You've probably done it yourself. You walk into a restaurant, you ask for a box at the end to take some food home. This server at this restaurant claims that about 30% of the people get the box but forget about it and leave it on the table when they leave. So they forget that they actually had the box. So suppose a researcher wants to challenge that claim, saying that they don't think it's 30%, they think it's something other than 30%. Well, the 30%, by the way, is a proportion, all right? 30% of people, right? We're counting the number of people and dividing by the number of people and that attend the restaurant. So 30% is 0.3. So here's the null hypothesis. The null hypothesis is basically that what the server is saying, we have 30%. P, which is the population proportion, is equal to 30 point. All right. Now, in this case, the challenge is that it's not 30%, it's something other than 30%. So we're going to say the alternative hypothesis is that P is not equal to 0.3. Okay. So not equal to 0.3. So these are the pair of hypotheses here. And according to the word problem here, says suppose the restaurant plans to take a random sample of 120 diners, and then they're going to count how many of them forget to take their leftover food. Okay. So that's going to be our the number of them out of the 120 who forget to take their leftover food home, divided by 120. That will be our sample proportion, and we're going to use that to test whether there's enough evidence to claim that P, the population proportion, is different than 30%. So the sample statistic we're going to use is P hat. That's the what we use. P hat is the sample proportion, and that will be the proportion that we get when we count the number out of the 120 who leave their box on the table when they leave instead of taking it. All right. So this is another example here. Again, just trying to give you some idea of the different types of examples we can see in hypothesis tests. Here's another example here. It says cocaine addiction is very hard to break. Even among addicts trying to break the addiction, relapse, which means going back to using cocaine, is common, right? So researchers try to find different treatment drugs to see if the relapse rate can be reduced. So they ran an experiment, double-blind experiment, and they compared the proportion that relapsed between those taking a drug being tested and those in a control group, which take a placebo, which is just some sugar water, right? The people taking it don't know the difference. All right, and the question is whether the drug reduces the proportion of addicts that relapse. All right, so P is the proportion that relapse. So a drug that works will reduce that proportion that relapse. So notice down here that the null hypothesis is that the drug has no effect. In other words, the proportion in the drug group that relapse is about the same as the proportion in the control group. The alternative hypothesis says that the proportion is less than in the drug group, less than that relapse than the proportion of that relapse in the control group. Well, that's the researcher's claim, is the drug works, right? So this is another example of an alternative hypothesis versus a research hypothesis. Now, the three types of hypotheses that we've looked at, one of them has a greater than symbol in the alternative hypothesis. One of them has a non-equal to symbol, and one of them has a less than symbol. Those are the three symbols that we will see when we have an alternative hypothesis, either less than, greater than, or not equal to. Notice that in all three cases, the null hypothesis always says equal to. All right? So that's one of the rules of when you create hypotheses, is that the null hypothesis says equal to, the alternative hypothesis will either say less than, greater than, or not equal to, depending on the wording of the problem. Again, you'll see plenty of examples of all of this. All right, so here's just a summary of what I just said. Notice again that the population parameters are always in the hypothesis test, the statement of the hypothesis test. In this case, P represents the population proportions, okay, not the sample proportion. We always have population parameters stated in the claims, in the null and alternative hypothesis. And again, the null hypothesis always has a statement of equality. The alternative hypothesis has one of these three cases: less than or greater than, not equal to, or less than. All right, so let me state a little bit about why we do a hypothesis test. And I'm going to use an example. All right. The example, I don't know if any of you have ever been on a jury. You're kind of young, but if you are eligible to vote, if you're registered to vote, you're also eligible to be on a jury. So you get a notice in the mail saying that you need to come to a certain place. And I guess with the pandemic, it would probably be a Zoom jury instead of something in person. But regardless, you do have to attend the meeting. And if you do get chosen for the jury, there are two types of trials, basically. There's the civil trial, which is basically a trial like somebody suing somebody else for maybe non-payment of rent or something like that. And then there's the criminal trial, the trials that we usually see on television on crime shows, like on Law and Order. Okay. Now, a criminal trial is where somebody is being charged with a crime, but the instruction to the jury is that you need to assume that the person is assumed innocent at first, okay? You don't assume that they're guilty at first. You assume that they're innocent. We can call that the null hypothesis. The null hypothesis is that person is assumed to be innocent, right? So what's the alternative hypothesis in a criminal trial? The alternative hypothesis is that they are guilty. Now, the whole idea is that the prosecutor, the lawyer who is arguing the case against the person who purportedly committed the crime, the prosecutor is trying to provide enough evidence so that it's beyond a reasonable doubt that the person committed the crime, and then hopefully the jurors all agree, and then they say, yes, the person, we think that there's enough evidence to convict the person. Okay. So the alternative hypothesis is that the person committed the crime, and then it's the prosecutor's job to present evidence, and then the juror's job is to weigh the evidence and determine if the evidence is strong enough to reject the null hypothesis that the person is not guilty, and to state that they are guilty and that they should be convicted. Okay? So a statistical test is just like that. We have a null hypothesis, then we have the researcher's hypothesis. And we always assume that the null hypothesis is true. And it's the researcher's job to provide statistical evidence to the contrary. And it needs to be strong enough so that we reject the null hypothesis and support the alternative hypothesis. Okay? So let's consider the case of the lunchbox, the restaurant box situation where there's leftovers in the box and people forget to take the box home. So suppose 120 people are being sampled, and here are, suppose 4 of you decided to randomly sample 120 people out of this restaurant, and these are the 4 results. In other words, one of you found 36 out of the 120 forgot to take the box home. Another of you found 37 of you forgot to take the box home. A third person in the class found 90 of the 120 forgot to take the box home, and then somebody else found 27 out of 120 forgot to take the box home. Now, the person in the server in the restaurant is claiming 30%, about 0.3 of them are forgetting to take the box home, about 30%. Now, let's take a look at these 4 different samples, and you can unmute and let me know what you think. Which one of these 4 samples would provide the most evidence that will reject the null hypothesis that it's 30% and will support the null hypothesis that it's not 30% of the people who are forgetting to take the box home? So take a look at the 4 results here. Tell me which of these 4 provides a lot of evidence, let's say, that the null hypothesis, it doesn't seem to be correct, and the alternative hypothesis seems to be correct. Does anybody have a guess at that? You can just unmute and yell out what you think.
Would it be C?
Yeah, that's right, C. C, 90 out of 120. I forgot. For that sample, that's a lot, isn't it? Actually, if you divide those 2 numbers, 90 divided by 120, that's 0.75 or 75%. You're absolutely correct. That is so much larger than P is equal to 0.3, 0.75, then that would be the one that seems to provide the strongest evidence that the null hypothesis is not correct, right? It just seems to be highly unlikely that 30% is correct for the whole population of people who go through this restaurant. When we have a sample of 120 and 90 of them are do not forget to take the box in. Now, let's take a look at the other 3 choices here. Which one provides the least amount of evidence? A, 36 out of 120, B, 37 out of 120, or D, 27 out of 120, which provides the least amount of evidence to reject the null hypothesis of 0.3. Again, anybody can yell out.
D.
Which one?
D.
D? Okay.
D.
Oh, D. Okay. Now, why did you pick D?
Because 27 forgot. So it's the least, I guess.
All right. Now, remember, we're dealing with proportions here, so you have to divide 27 by 120. So look, what does that come out to be? Person who was answering the question, you have a calculator right near you. I'm actually doing the same thing here. 27 divided by 120, what did you get?
0.225.
All right. Now, that is somewhat different than 0.3, correct?
Yeah.
Now, remember, the alternative says not equal to, so it could be on the low side or high side that we're talking about here, right?
Hmm.
So certainly C is much different than 0.3. 0.225 is different, but it's not, we're not really sure whether it's different enough to say we have enough evidence to reject P is equal to 0.3. So you're sort of right in a sense, but there's another answer here there where we could absolutely say there's definitely very little evidence or not much evidence to reject the null of 0.3. And which one is that? It's not D, because D is different than 0.3. Anybody have an idea which one it would be? One of the first two.
A.
A, yeah. Because 36 out of 120 is 0.3, isn't it? It's not, it's definitely equal to 0.3. So that certainly provides the least amount of evidence, right? 37, of course, is also pretty close to 0.3. That would be probably come in number 2. And then the third one would, the third one would be 27, the one we mentioned earlier. That one, I would say we would need to do some sort of statistical work with that, because we're not really sure. It's sort of like it is different, but we're not sure whether it's different enough. D. C, definitely, that one is definitely provides the strongest evidence. So here's the whole idea. We're looking for those extreme answers that are different than the null hypothesis. Those that are more extremely different than the null hypothesis in our sample supports that supports the idea of rejecting the null hypothesis. Okay, so anything that's close to 0.3, we have to do some sort of statistical test because we're not quite sure if it's close, if it's far enough away. Now, the one that's, answer A, where it's exactly 0.3, that certainly doesn't provide much evidence that the population is different. The population proportion is different than 0.3, right? That one provides at least enough. All right, so you get the idea, hopefully, that we're looking for some extreme results here that will determine whether we reject the null hypothesis. Right? Okay. And again, the book goes through this. There's a video solution that you can read, look through. Of course, you have to go through the ebook to look at all that. All right. Now, hypothesis tests are done on all sorts of parameters, not just means and proportions. You can have hypothesis tests on correlation coefficients. All right, you can have it on other things that you haven't even learned about yet. But in this course, we're going to strictly look at hypothesis tests for means, hypothesis tests for proportions. Okay, they show an example here for correlation coefficient. And they're really saying is, all right, we have a sample. We've compared two quantitative variables that should look familiar to. It's a scatter plot. We're determining if the correlation between those two variables is significantly different than 0. Because this is from a sample. And somebody else could have another sample which shows different results, different correlation coefficient. So we can do a statistical test on this, and the hypothesis test could look something like this. Now, you probably don't remember, but I mentioned it briefly that for the correlation coefficient, we use a Greek letter rho, R-H-O. That's what it looks like. It almost looks like a P, to represent the population correlation coefficient. All right. And in this case, Whereas the null hypothesis is the correlation is 0, and the alternative hypothesis it's a positive correlation, right? Something significant. So there would be a hypothesis test that we could do for this one also. Now, we're not going to do it in this course. All right, we're not going to be dealing with testing whether a sample correlation coefficient is significantly more than 0, but that's something that could be done if somebody wanted to. All right. Okay. Now, here's another example here of a study. This has to do with arsenic in chickens. Now, this is a little scary when you read it because in the European Union, arsenic additives that are added to chicken feed, fed to chicken, are banned, but it's not banned in the United States, which is kind of scary. But so many of the chickens that are that you get in restaurants could have arsenic in it. Now, the question is, how much arsenic is safe? Well, according to the USDA, the United States Department of Agriculture, anything less than 80, what is 80 here? Parts per billion of arsenic in the feed, I guess in the chicken itself, is considered safe. Anything more than 80 parts per billion is considered unsafe. So if you read all of this up here, it says a restaurant chain says that it will cancel its relationship with any supplier of chickens where the average amount of arsenic in the chickens is more than 80 parts per billion. So what are they going to do? They're going to check every single chicken that comes from their suppliers? No, they're going to do a random sample chickens, check for arsenic. And if a sample has more than 80, if the sample has a mean average amount of arsenic in their chicken of greater than 80 parts per billion, they're going to cancel their contract with that supplier of chickens. Okay, so what is the null hypothesis? 80 parts per billion. Now you might say, well, why not less than 80? Well, you could have stated less than or equal to 80, but the way we set up hypothesis tests, we always do the null hypothesis as equal to. Even if we mean less than or equal to, we put an equal to there. And then the alternative hypothesis is that the population mean is greater than 80. Now remember, we are taking a random sample of chickens from that supplier. So it is possible that whatever result we get, it could be greater than 80 for the average amount of that sample of chickens. It's possible that the overall population of chickens that come through from that supplier is less than 80. So we have to do a statistical test, all right, which you'll learn how to do. But the alternative hypothesis for this particular case is that the mean is greater than 80 because that's what the supplier wants to test if they want to cancel that relationship with what the chicken chain wants to test to see if that supplier, they want to continue having a business relationship with that supplier. So the alternative hypothesis is mu is greater than 80. And if we do reject the null hypothesis and accept the alternative hypothesis, then this chicken chain will cancel that supply of chicken from that supplier. They're just going to go with somebody else. All right. So anyway, that's an example of where we use it in business, hypothesis testing. It's not just used in research, it's used in business also. Now, suppose these are 3 suppliers who provide chicken to this chicken chain. Take a look at the 3. These are dot plots. Take a look at the 3 of them. Notice that the vertical bar is at 80. This is measuring the amount of arsenic for these samples of chickens. Take a look at the 3 suppliers. Tell me which one provides strong evidence. Let's just look at the here's the null and alternative hypothesis. Here we go. I think we can see all three of them now. All right. The alternative hypothesis is that mu is greater than 80. Which one of these provides the greatest support for the alternative hypothesis that the mean is greater than 80? Is it supplier 1, supplier 2, or supplier 3? Again, you can unmute. Tell me which one seems to reject the null hypothesis that mu is equal to 80 and seems to support that it's greater than 80. Which one of these dot plots seems to support that?
3.
3. Yeah. Notice that out of all the, now every little circle there represents a chicken in the sample, right? Notice that the smallest amount of arsenic are those 4 chickens that are right at 80, right? All the rest of them have greater than 80. Which one provides the least amount of evidence to reject the null hypothesis? Is it supplier 1 or supplier 2? Which one provides the least amount of evidence to support the alternative hypothesis that the mean is greater than 80? Which one is it? The least amount of evidence. Is it supplier 1, supplier 2? You know, supplier 3 provides the most amount of evidence to reject it. Which one provides the least amount of evidence?
Supplier 1.
Oh yeah, supplier 1, right? If you look at it, out of all those circles there, only 7 out of them are 80 or above. Most of them are below 80. So the least amount of evidence is supplier 1. The most amount of evidence to reject the null hypothesis is supplier 3. We're not really sure about supplier 2, right? That's sort of in that in-between area where we would have to do some sort of statistical test. All right, so I hope you're getting the idea now of exactly what we need to do when we do a statistical test, right? Now remember, in this case, the alternative hypothesis is that the mean is greater than 80. So what are we looking for? We're looking for lots of dots that are bigger than 80. Okay, so that provides the most evidence against the null hypothesis, which means that if most of the dots are below 80, that would provide the least amount of evidence. And this middle one here is sort of like we're not sure. So we definitely have to do something like a statistical testing. All right, any questions? So this is giving you sort of an idea of that a hypothesis test has 2 hypotheses that are competing. One is called the null hypothesis, always has an equal sign. The other is called the alternative hypothesis, which is either going to be less than, greater than, or not equal to. And what we're looking for is extreme results in our sample, which allow us to reject the null hypothesis and support the alternative hypothesis. That's what we're interested in. All right, now, so far we've just looked at plots and sort of guessing, right? Which of the, like in the one we just did, those 3 dot plots here, we were sort of like guessing, right? But statistics is more than guessing. We have to come up with something quantitative, which helps us make a decision about whether we can reject the null hypothesis. Section 4.2 comes up with a new concept, which helps us do that. And I think I might have to reboot this. Oh, how about that? It worked. So we're going to come up with this new concept, a quantitative concept called p-values. P-values actually are used not only with beginning students, but it's used by people who do very advanced research at the PhD level, or at the level of a medical doctor, something on that very high level. So p-values are introduced here, and I can tell you this book does a great job in helping you understand what a p-value is, because most students have difficulty with this using other textbooks, because this information about p-values is just thrown out there and students are left pretty much on their own to try to figure out how it works. However, this section here helps us understand how to use p-values to determine whether we should reject the null hypothesis and support the alternative hypothesis. All right. Now we're going to go back to this case here where we have two hypotheses for the two groups of mice. Remember the light group and the dark group. Remember the light group is where they put the light on at night dimly, but they put on the light on at night with the group of mice who are getting that treatment. And then the dark group, they just turn the lights off. Okay. And they want to see if there's any adverse effect of having the light on at night. And they're measuring it by looking at the gain in body mass, the gain in weight of the mice. And they're proposing in the alternative hypothesis that there's a mean, that the mean gain in weight of the mice is bigger for the group that gets the light at night versus the group that's getting this regular dark conditions. Okay. Now the sample data is down here. Again, they show it to you again. Notice that the light group at the average of the gain, the body mass gain for the 10 mice is 6.732 in the light group, and the average for the 8 mice in the dark group is 4.114. If you subtract these two means, you end up seeing that for the sample of 18 mice, that the light groups, the average of the weight gain for the light group is 2.618 grams bigger than the average for the dark group. Okay. So we want to know whether there is any significant, this 2.618 is significantly big enough to say we don't think the alternative hypothesis is true. We think the null hypothesis is true. We think there is the light group does have a bigger mean than the dark group. All right. So we want to look at the sample and say, is this 2.618 big enough to make that come to that conclusion? That's really what we're trying to do here. So remember, the people who created this textbook created StatKey. And in addition to coming up with a way of looking at confidence intervals through the bootstrap sampling distribution, if you remember that from last week, they came up with a new type of distribution called a randomization distribution, again, using simulation. Now, I'll show you next time on Wednesday how this works in StatKey. But for now, assume that just like we did with confidence intervals, we can create a dot plot that looks like this with 3,000 samples. Each of the samples is for the 18 mice. And what we're going to do is we're going to assume that there's no difference between the weight gains in the light group and the dark group. In other words, we're going to assume the null hypothesis is true. Notice that when we create these samples of size 18, the 3,000 of them, there's 3,000 dots here. Notice that the average in the middle is 0. Right. So the way that these samples are created, they're created so that the overall average is close to 0. And notice it's 0.009 here when they take the average of these 3,000 samples, that's close to 0. And then they come up with a standard error here, 1.288. All right, anyway, this is what's called a randomization sampling distribution. Okay, 3,000 samples in this case here. And we just want to see if we randomly created these 3,000 samples, what would be the range of possible differences between the light group, the mean of the light group, and the mean of the dark group? For example, anything that's negative here, remember what we're measuring here is the mean, the sample mean of the light group minus the sample mean of the dark group. So if it's negative, it means that the dark group's average body mass gain is bigger than the light group, because the light these numbers down here is the light average minus the dark average. So if it's negative, that means the dark average is bigger. Anything that's positive means that the light average is bigger than the dark average. Okay. So we create this distribution. Now we're going to do a test. We're going to test to see, look at the one average, the one sample average that we got, which was the one that we got before, and see if it's something that's extreme compared to all these other dots that are here. Extremely different than what? Extremely different than 0. So let's just scroll down here and just, and by the way, this other table that they have here is a case where they did a randomization sample. And in this case, they're showing that in this particular sample, it's one of these 3,000 dots, that the dark group's average is bigger than the light group's average in this case here. And so the difference would be a negative number. All right. They showed it right down here. So they just want to show that many of these dots are negative. Some of these dots are positive. All right. Now, suppose we have two different samples. All right. Suppose somebody actually ran a sample, and suppose they came up with and this is a real sample. Let's say one of you ran one of these experiments with the 18 mice, and you found that the difference between the group of mice that are in the light group and the group of mice that are in the dark group, the difference in their average body mass gains is 0.75. Okay. Suppose somebody else in the class did the same, randomly assigned 18 mice, and their difference is a difference of 4 grams between the light group and then the group that's in the dark group. All right, the group of mice in the dark group. So the question is, which one of these would have would support the idea that the light group has a bigger average body mass than the dark group body mass gain? So what we could do is, actually, I think I could scroll down here. We could actually recreate the randomization distribution that was created above. Okay. And suppose, remember the middle, what's in the middle here is 0. So where's 0.75 in relation to it? Suppose it's over here. Suppose it's here. Suppose that 4.0, the other sample, is way down here. Now, which of these two samples provides more evidence that the light group has more, the light group, the mice in the light group gain more body mass than the mice in the dark group? Which one of these provides more evidence of this? Is it the difference of 0.75 or the difference of 4? So go ahead and again, you can unmute, tell me which one provides more evidence of rejecting the null hypothesis that says two groups are about equal, and then accepting that the light group has a bigger body mass average. Which one of these would support that better? Remember, the null hypothesis is that there's no difference between the two groups. So what's being measured down here along the x-axis is the difference between the light group and the dark group. So 0 is in the center here. 0.75 would be around here. 4.0 would be further down. So which of these provides more evidence against the null hypothesis that the two groups have about the same body mass gain? Not sure?
The second one?
The second one, of course. The second one, because it's further away from the null hypothesis value of 0. See it? This one at 0.75, where the arrow is pointing here, is closer to 0. So the whole idea is, you have to think about it a minute. if there's normal variation around a population mean, in other words, if the samples vary around the mean, but most of them are close to the population mean, the ones that are further away are less likely to occur, right? If we assume the population mean. Now, in this case, it's a difference of means between the two groups. So we would say that when the difference is 4, it would seem highly unlikely that the true population difference is 0, because it's how many of these dots are less than that are at least 4. How many dots do we see here? There's only like 3 or 4 of them, right, down here. While there's many more dots, samples that have values that are at least 0.75. So it seems more likely with 0.75 that could be normal variation of samples. All right, normal variation based on the idea that the difference in the means is 0. We're going to see some samples that are going to be bigger than 0, some samples going to be less than 0, but it seems more likely that a sample difference of 0.75 would be due to normal variation. This 4 here, hardly any of the dots that are at 4 or larger. That means it seems to be more unlikely that the population mean, or the difference in the population means here is 0. Seems more unlikely. So here's the whole idea. What if we wanted to determine the proportion of these randomization samples that are as extreme or more extreme than the sample result that we got? That measure, that proportion, the larger that proportion is, the less likely we would reject the null hypothesis. It would seem to be more consistent with just normal variation samples. The smaller the proportion of samples that are at least or more than the value of the sample statistic, the smaller that the proportion is, the more likely we would reject the null hypothesis. In this case, that the difference in proportion, the difference in means is 0. All right. So what is the p-value? The p-value is the proportion of samples. If we assume the null hypothesis is true, now a randomization distribution, the way they set it up in Stackey, they're assuming the null hypothesis is true. If we calculate the proportion of samples out of the 3,000 samples in this case, that would give us statistics as extreme or more extreme than the observed sample. If that p-value is really small, that would support the idea that the null hypothesis is not true, that it's probably the alternative hypothesis that is true. If the p-value is larger, that would provide less evidence of rejecting the null hypothesis, because it could just be due to normal variation, that sample, right? So in the example that we just gave, suppose we look at the original sample, where we saw the difference between the light group and the dark group of 2.618, right? That was the original sample. Let's just scroll back up. We were talking about this here. This is the original sample that was done. And we take the difference between the light group's sample mean and the dark group sample mean. We got 2.618, I believe. 2.618. Okay. All right. Now, the question is, what is the p-value for that particular sample? So what would you do? Well, you create your randomization distribution, like we did before, and we would find 2.618 on that along the curve. So 2.618 would probably be down here somewhere, right? I mean, if this is 0.75 and this was 4, well, 2.618 is probably in between somewhere. And then we count the number of samples that are at least as big as 2.618. Divide that by 3,000. So we actually counted 53 of those dots or samples that have sample mean, have differences of sample means of at least 2.618. We counted 53 of them, divided by 3,000. Notice that the proportion is 0.018. Okay, so for the actual sample that we got, there is a 1.8% chance that the sample, the difference in the population means is 0, and there's a 1.8% chance of getting a sample that looked like this, where the difference in the sample means is 2.618. So it seems highly unlikely, doesn't it? There's only 1.8% chance of assuming that the difference in the population mean between these two groups is 0, and getting a sample that looks like this. Okay, getting a sample as extreme as this, only 1.8% chance. So this sort of supports the idea that we should reject the null hypothesis that the two means are different, or the two means are the same, and we're going to support the idea that the light group's mean is bigger than the dark group's mean. Okay, so the smaller the p-value, the more support we have for the alternative hypothesis. That's the whole idea. Right? Okay, and by the way, here it is right here. There's a very nice way of doing this. I'll show you next time with StatCake, is show you how it works in StatCake. But anyway, here's 2.618. Here's the 0, the null assumption of 0. And notice that the red dots here represent all of the sample differences in means that are at least 2.618, and therefore, and there's 53 of these. We divide by 3,000, and this gives us our p-value 0.018. So it's a small p-value. All right. So here is the whole idea of using p-values. And again, we will practice more. If this seems, if you're a little cloudy on this, unsure, that is okay. We will do more examples, all right? So p-values from a randomization distribution. To find a p-value, we find the observed statistic, that's from the actual sample. We, of course, create the randomization distribution, and we find where along the curve is that particular observed statistic. In this case, 2.618 is right over here, right? All right. And we find the number of samples that are at least as extreme as that one. Okay. And we count the number of samples that are at least as extreme, and we divide by the total number of samples in the randomization distribution, and that gives us our p-value. The smaller the p-value, the better chance that we will reject the null hypothesis. Now, I will give you a formula in chapter 6, I think. Actually, I think it's in chapter 5. So next Monday's class, I will show you, and actually maybe even be Wednesday's class. I'll have to look. But very soon, I will be showing you an exact thing that we do with the p-value. We're going to compare it to another number, and we'll know exactly when we should reject the null hypothesis. So that will become clear next time. All right. We'll go over it. Now, the alternative hypothesis determines where we test the p-value. Let me make this clear. Now, remember, the alternative hypothesis has 3 possible symbols. It has greater than, less than, or not equal to. Now, in this case here, the alternative hypothesis was greater than. The light group was bigger, the mean of the light group was bigger than the mean of the dark group. So if it's greater than, we're going to look at the p-value. We're going to look at the right tail, all right, because it's greater than. We're going to look out here. For examples where we have less than, where the alternative hypothesis says less than, we're going to look at the left tail. And then the special case, and I'm not going to go through it now because it'll just add more confusion to you right now. But when we have not equal to in the alternative hypothesis, we're going to be looking at both tails, the left tail and the right. That's not something we're going to do right now. Anyway, are there any questions? Any questions? Okay, just looking at what else is here. And yeah, I'm not going to get into this right now. I'll go over it next time. We'll do the case where there is two tail, where we have two tails. So we'll do that next time. No, there's no case, there's no questions, nothing. Okay, now I'm going to go over this next time. I'm going to also go over section 4.3 and 4.4. 4.3 will be more examples of how to use randomization distributions in StatKey, how to come up with p-values, all that sort of thing will be done next time. I'll actually show you how it works in StatKey. I'm just giving you a short introduction. But before I do that, I will go over this little box here, which will talk about the three types of tests, depending on the symbol in the alternative hypothesis, greater than, less than, or not equal to. There's three types of tests. I'll go over that next time. That'll be the first thing we'll do next time. I don't want to do it now. And I want you to start reading this chapter, all right? It's very important to read this. You don't read it, and you're going to forget what I said in class. Now, of course, this is all going to be recorded. And I believe I started the recording. Yes, I did. So it's all going to be recorded. It looks like we do have a couple chat messages here, so let's see what people are saying. All right. Okay. All right. I guess this was just answers to questions from before. All right. We'll go over a lot of this next time. All right. And how to use the p-value. All right. Are there any questions? Because I know this was a lot of new stuff. But again, I highly recommend that you read these two sections, 4.1 and 4.2, before the next class. Even if you only understand 20% of it, 30% of it. Don't worry, we're going to do enough repetition so that it'll become more understandable to you, all right? Next time, we're going to go over 4.3 also, and we're going to go over a little bit of 4.4. The homework will be 4.1, 4.2, and 4.3. There won't be any homework for 4.4. And then next Monday, we're going to go over 5.2, which we'll start using more formulas to do hypothesis tests, just like we did in section 5.2 for confidence intervals. All right. No questions. I think you're all probably hoping this will get easier, but it will. Don't worry about it. It will get easier. Again, I like the way the book does this, but you will have to do some reading, no doubt about it. Yeah, you'll have to read the textbook. And don't worry again how much you understand. Just read it so that you're familiar with what the book is saying, because they do a very good job. Believe me, most textbooks do not do a good job. All right, so that will be it for today. I'm just going to stop a little bit early because I don't want to jump ahead too much. As far as attendance is concerned, Zoom does record who is here. And to get attendance, by the way, to get credit for attendance, you have to be here for more than, I'd say, 3/4 of the meeting time. It does record how much you are recorded. So if you come in and you're only here for 5 minutes, that's not evidence that you were here the whole time. All right, so please get here on time. And to get credit, again, you need to have a significant part of the Zoom session. You need to be here. All right. Stop sharing. Any questions? No questions? All right. So that's it for today. I'm going to stop the recording, and I will, again, we'll be doing this on Thursday, more of this on Thursday. Again, it's recorded, so you'll be able to re-watch it, just like the recordings I'll be doing next week. All right, that you'll start seeing next week. They'll all be recorded. All right, no questions. So I will again see you next time. Again, at the same time at 12:30. All right, take care.
Happy Hour, Professor. Thank you.
You too.